Okay, let's go ahead. Let's go ahead and get started. Is my voice being amplified? It is. A little bit? Tiny bit maybe? Yeah. Okay. Oh, now my voice is doing it. Okay, let's go ahead and get started. Just one administrative announcement before I get started. Problem set 4 is here for you to pick up. Actually, let me ask a question. So it has come to my attention that classical mechanics has scheduled the exam the same day. You changed the classical mechanics. Perfect. Okay, good. I was playing a little game of chicken with Robert, and sounds like he blinks first. Okay, good. But unlike chicken, you guys are the ones who are being held hostage instead of me. Okay. Okay, let's continue with our discussion of energy and momentum in special relativity. So last time I gave a bit of an argument that in special relativity, the energy and momentum of an object whose mass, as measured in a frame where the object is at rest, is equal to m, and velocity v, as measured in some particular reference frame, then the energy and momentum are given by the formulas E is equal to mc squared divided by the square root of 1 minus v squared over c squared. So that's just the gamma factor associated to the velocity v. And the momentum is that gamma factor times the usual Newtonian momentum, m times v. So the conservation then of energy and momentum will then form some of the basic core principles of dynamics and special relativity, just as they did in Newtonian dynamics. And one of the things which I emphasized yesterday and would like to mention again today is that the conservation of energy and momentum is really a postulate of the theory of dynamics, rather than a consequence of the theory of dynamics. And so there's a sense in which we really shouldn't be able to derive these. One could only come up with different ways of formulating the postulates of our theories of dynamics. So I could postulate, for example, that energy is conserved in my theory of dynamics, or I could postulate that my theory of dynamics obeys something like Newton's laws, and then I could see that these two different ways of thinking about dynamics are the same. But there is a sense in which we can't, in any precise sense, derive these formulas for the energy and momentum. But we can, at the very least, justify them. And so what I did last class is I gave you a pretty good argument for the conservation of momentum. And then I used our definition of force and our definition of work to give you an analogous way of thinking about energy. And what I'd like to do today is give you a slightly different and perhaps a little bit more hands-on way of deriving this formula for energy in special relativity, given the formula for momentum. So I gave you a derivation of this formula for the relativistic momentum last class. And now I'd like to provide a simple thought experiment which will allow us to understand the origin of this formula for energy in special relativity. Okay. So this will also give us a chance to get our hands dirty excuse me, and understand some of the implications of this form of relativistic energy. Excuse me. So let's imagine that we have two objects of equal rest mass that I'll call little m that collide with equal and opposite velocities. Okay. So we could consider this problem in the frame where the two objects have equal and opposite velocities. So there's one object, there's the other object. They're approaching each other at some velocity v, and after they collide, we'll just say that they form some second object with a mass that I'll call capital M, and because of my choice of frame, this mass is going to be at rest. You can easily see that the conservation of momentum tells us that if these two objects are colliding with equal and opposite velocity, then the total momentum of the system is zero, and so afterwards, if they just form one mass, that mass cannot be moving. And because of our formula for energy, we then expect that in special relativity, this final mass will not be equal to twice little m, the masses of the initial objects, but will be somewhat greater to reflect the relativistic energy contained in these two masses as they move at velocity v. So, in order to analyze this problem, let me introduce a different frame, and this will be the frame where one of the masses is initially at rest. So this is a frame S prime, which is moving with velocity v with respect to S. So from the point of view of an observer in this frame, one of the initial masses will be at rest, but the final mass m will not be at rest. It will be moving with velocity v, because S and S prime are related by some velocity v. So in this frame, we could calculate the velocity v prime of the mass little m, which is moving, and that's just given by the velocity addition formula. So it'll be 2v over 1 plus v squared over c squared. That's just the velocity addition formula. And then I can use momentum conservation in the frame S prime. So what does that tell us? That tells me that the initial momentum, which is the gamma of v prime, so 1 over the square root of 1 minus v prime squared over c squared, times mv prime, so that's the initial momentum of the system, has to be equal to the final momentum of the system, which is gamma of v times big M times its velocity v. And I'm being careful here to remember that because there's more than one velocity at play here, there's v and v prime, so whenever I write down gamma, I need to be careful to tell you which velocity I'm talking about. So I'm writing gamma of v or gamma of v prime. So this will allow me to solve for big M. In particular, big M divided by little m is going to be equal to gamma of v prime times v prime over gamma of v times v. And then I can go ahead and plug in my formula for v prime. And what do I get? Well, what's v prime over v? That's easy just using this formula. That is 2 over 1 plus v squared over c squared. What's gamma of v prime over gamma of v? Well, that's a little more complicated. It's the square root of 1 minus v squared over c squared divided by the square root of 1 minus v prime squared over c squared. What's that? That's 2v over 1 plus v squared over c squared, squared, all divided by c squared. So let's just work this guy out. So multiplying this 1 plus v squared over c squared in the denominator into the square root, we get 2 times the square root of 1 minus v squared over c squared in the numerator. And then in the denominator, we have the square root of 1 plus v squared over c squared quantity squared minus 4 v squared over c squared. And if you expand out that 1 plus v squared over c squared quantity squared in the denominator, you'll see that all that minus 4 v squared over c squared does is it changes the cross term plus 2v squared over c squared into minus 2v squared over c squared, so that that term in the denominator is just the square root of 1 minus v squared over c squared quantity squared, otherwise known as the square of the numerator. So this is 2 divided by the square root of 1 minus v squared over c squared. I went through the algebra a little fast there. It's very similar to algebra that you've seen many times before in this class. So if it wasn't clear, maybe you can go through it again by yourselves, or if there's something that was abundantly unclear, you could ask me. It's just straightforward algebra. Okay, so what does this mean? This means that the final mass was twice the initial mass divided by the square root of 1 minus v squared over c squared. So in terms of the frame S, we have two objects of mass m, which are colliding with each other to form an object of mass big M, which is at rest. And we see that big M is not twice little m, but it's something bigger than twice little m. It's twice little m divided by this factor, 1 minus v squared over c squared. And so that allows us to see that energy is conserved in this process only if we identify the energy of one of these initial particles as mc squared divided by the square root of 1 minus v squared over c squared. And that is, of course, the same formula for the relativistic energy that we derived last time from a slightly different point of view, thinking about works and forces and so forth. So this is a specific example where we can see that that energy, that our form for the conservation of momentum in the S prime frame turned into a formula for conservation of energy in the S frame. Question?
Okay, for the momentum of the M, could we also find the momentum of each particle at a speed, and then just add them?
I guess I'm not quite sure exactly what you mean. So when I talk about the left and the right-hand side of this equation up here, I mean, I haven't worked out the left and the right-hand side of this equation up here are the initial and the final momentum in the S prime frame. And when you write that down, you sum over all of the things, all of the particles in your system, all of the objects. But before the collision, there are two objects, one of which is not moving, so it has zero momentum. Of course, we could also work out the momentum in the S frame rather than the S prime frame, but that momentum is just going to be zero, because you're going to have a gamma mv for a particle moving this way, a gamma mv for a particle moving this way. They're going to add up to zero because the velocities are equal and opposite. That's another way of saying that I just chose my frame S so that at the end of the day, my big mass M is at rest. And an object at rest has energy but not momentum. Question. Good question. Any other questions? Okay. Just as a way of getting familiar with the way these sorts of things work, let me just check the conservation of energy in the S prime frame. So in the S prime frame, we had a particle of mass m moving at velocity v prime, colliding with another particle at mass m, giving me something of mass big M moving at velocity v. So let's just check and see that this conserves energy. Okay. This is the sort of exercise that I think it's worth going through at least a couple times to convince yourselves of the correctness of this description. So what is the energy before the collision process? Well, we have the energy of the guy at rest, so that's mc squared, plus the energy of the guy who's moving, which is gamma of v prime times mc squared. And we want to know whether that's equal to the energy of the final mass m, capital M, moving at velocity v, which is gamma of v times mc squared, or using our formula for capital M up above, this is twice little m times gamma of v squared times c squared. Okay, and we're asking whether those two sides are equal. So let's go ahead and work out the left-hand side of this equation. So all of the factors of mc squared are going to factor out. So we just need to calculate 1 plus gamma of v prime. What is that? That's 1 plus 1 over the square root of, here, let me write it slightly differently. Let's write it as 1 plus 1 over the square root of 1 plus v prime squared, or 1 minus v prime squared over c squared. So that's 1 minus, and what was v prime? Remember, it was 2v over 1 plus v squared over c squared, okay? So 1 plus gamma of v prime is 1 plus 1 over the square root of 1 minus v prime squared over c squared. Ooh, I forgot a c squared there. So let's work that out. That's 1 plus, let's pull out a factor of 1 plus v squared over c squared from the denominator there. So that'll be 1 plus v squared over c squared divided by the square root of 1 plus v squared over c squared squared minus 4v squared over c squared. Okay. And then there's another cancellation there. So you expand out 1 plus v squared over c squared quantity squared. You get 1 plus 2v squared over c squared plus v to the fourth over c to the fourth. And then subtracting off 4v squared over c squared changes that into 1 minus v squared over c squared quantity squared. And so what do we get? We get 1 plus v squared over c squared over 1 minus v squared over c squared. And then you can collect the terms there. So what is that? We could write that as 1 minus v squared over c squared plus 1 plus v squared over c squared, all divided by 1 minus v squared over c squared. Those v squareds over c squared cancel, and you get 1 over 1 minus v squared over c squared, otherwise known as gamma of v squared. And indeed, that's precisely what we need in order to get the conservation of energy in the S prime frame. Yes, question?
You missed a factor of 2.
2. I missed a factor of 2. Yes, there are 2 1s. 1 plus 1 is generally accepted to be 2. Thank you. Yes?
Why should energy be conserved? It's an inelastic.
Okay. Well, energy is always conserved, okay, in an inelastic or an elastic collision.
Yeah, but, I mean, if we were doing this in just classical mechanics, we'd say that energy was not conserved. I mean, obviously there's noise, but...
Well, okay. If you had I mean, in classical mechanics, you often distinguish between elastic and inelastic collisions, depending on whether things stick together or they bounce apart or stuff like that. But you never violate the principles of conservation or energy or momentum in classical physics. What you do sometimes in classical physics is you fail to keep track of all of the various parts of the system that would contain energy and momentum. Things like the internal properties of the objects that you're colliding. Like if you take two balls of silly putty and you collide them together, then they'll form another ball of silly putty with twice the mass, but it'll be slightly hotter, okay? Because of the kinetic energy will get transferred into the internal degrees of freedom of the silly putty. In special relativity, when we talk about the mass capital M, it's really keeping track of all of the energy that is contained inside these balls of silly putty. Okay, and as we'll see, actually, in the next 5 minutes, in fact, energy and mass are sort of indistinguishable in special relativity. So I'm not sure if I've answered your question in complete satisfaction. But let me continue for just a minute or two, and then you can feel free to ask again if it's still not clear. That's a good question, actually. To some extent, the use of conservation of energy and momentum is one of those fundamental principles of physics that, is actually wrong, but is much more right than inelastic, that business about inelastic and elastic collisions. Okay. Turns out that, as we'll see later in the course, when we consider cosmology, at least very briefly, there's a sense in which energy is not exactly conserved. Okay. Something more subtle happens. But if you fail to take into account the expansion of the universe, then energy is conserved. Any other questions? By the way, are you guys okay that I'm skipping the occasional step here in this derivation? I think we're all adults here. I don't necessarily need to go and cancel every factor of 2 and minus sign. We're all capable of doing that on your own. But if at some point I end up going way too fast and really confusing you completely, do let me know, because I can always go through and fill in a few of the intermediate steps. Okay. So, there's an important point which I really want to emphasize here, which is that the energy of an object, gamma mc squared, and the momentum, gamma mv, depend on the frame in which they are measured. And we're already used in this class to dealing with quantities that depend on the frame in which they're measured. If you have a pair of events, then the time separation between those events and the spatial separation between those events will likewise depend on the frame in which they are measured. And in fact, it's not just a coincidence that E and P depend on the frame in which they're measured in a similar way that delta T and delta X depend on the frame in which they are measured. And so it turns out that there's a very, very close relationship between the properties of E and P as one changes one's reference frame and the properties of delta T and delta X that we have already observed. Okay. And in fact, this is one of the most fundamental properties of special relativity, and one that I'll develop for the rest of this class. So the first thing that I would like to ask, however, is if the energy and the momentum are dependent on the person who is doing the measurement, on the frame in which they are measured, then is it possible still to define some notion of the energy of an object or the energy of a system which is independent of the frame in which they are measured? We saw in the case of time separations and spatial separations that even though delta T and delta X individually were frame dependent, there was a combination of them which was independent of the frame in which they were measured. And it was this combination which had real physical meaning independent of the reference frame in which one performs a measurement. So let's now ask whether there's a similar combination of E and P which has a physical meaning independent of the frame in which the energy and momentum are measured. So let's stare at those formulas for E and P a little bit. And let's consider the following combination of E and P. Let's consider E squared minus P squared C squared. So what is that? Well, E is gamma MC squared, so that is gamma squared M squared C to the fourth, minus P squared is gamma squared M squared V squared times C squared. I included that factor of C squared just in order to get the dimensions to work out. Remember that energy has units of mass times velocity squared, whereas momentum has units of mass times velocity. So when comparing energy and momentum, I'll always need to include a factor of something which has dimensions of velocity. Okay, so what is that? Let's collect the terms. That's gamma squared times 1 minus V squared over C squared times M squared C to the fourth, otherwise known as M squared C to the fourth. M is the rest mass of the object, and so this is frame independent. And in particular, it is just the rest mass or rest energy of the object. So just as in the relativity of length and time, we saw that there was an invariant interval between two events that was independent of the observer. We see that if you have an object, then although its energy and momentum can depend on the reference frame in which one measures it, this combination, which is the rest mass of the object, is independent of the frame in which it's measured. And this equation is sometimes rewritten in a particularly suggestive form. So it's rewritten as E squared is M squared C to the fourth plus P squared C squared. This is an equation which allows you to think of the energy of the particle as a function of its momentum. And it is referred to as the dispersion relation of a particle in special relativity. So, just as in Newtonian physics, we have a formula for the energy of a particle, which would be its rest energy, okay, which is usually set to 0 by convention, but might not be equal to 0. I could attribute to that rest energy, for example, the kinetic energy of the thermal ensemble of particles in the silly putty in the example that we were discussing earlier, plus the usual kinetic energy, 1 over 2m p squared. So the Newtonian relation, E is equal to 1 over 2m p squared, or E is 1/2 mv squared, is replaced in special relativity by the relativistic equation, E squared is m squared c to the fourth plus p squared c squared. And as we checked essentially last time, one could always expand this formula, this dispersion relation, at small velocities by doing a Taylor expansion in V over C. And you would see that if you compare to Newtonian physics, you would find that the rest mass of the object is mc squared. The first correction, when the velocity is small, is the usual Newtonian term, 1 over 2 mp squared. But then there would be higher order corrections coming from special relativity. So, This way of writing the dispersion relation of special relativity is particularly interesting because it allows us to consider objects such as photons, namely particles of light, which have rest mass equal to 0. So that E squared is P squared C squared, or E is P times C. I suppose I should technically write the absolute value of P times C there. Let me write it like that. So, for example, one of the lessons that you may have learned about light in your elementary classes on waves is that for a light wave, or for a photon, the energy of the photon is Planck's constant times the frequency of the photon, and the momentum is Planck's constant times the frequency divided by the speed of light. Have you guys seen that formula before? I assume you've seen the formula for the energy at least. Have you seen the formula for the momentum? Good. Well, when you were studying that formula, believe it or not, although you may not have realized it at the time, you were also studying the relativistic relationship between energy and momentum. And you see that they satisfy precisely the correct relativistic relationship. And for everyday objects, of course, the rest energy, mc squared, is absolutely gigantic. So, for example, if you put in the numbers, a kilogram is about 10 to the 17th joules. I looked it up. That's roughly the power consumption of the city of Montreal in 1 year. Okay, it's a lot of energy, at least in everyday terms. And so you see that if you start considering relativistic processes like this, where energy like this can be released in terms of normal kinetic energy, then the possibilities of that are quite interesting. So let's consider the example that we had over here, where we had two objects with small mass colliding together to form some big mass. Okay. Let's consider the reverse of that process, where you have a big mass splitting into two smaller objects of littler mass, moving with some velocity. So if a process is allowed, then the time reverse of that process should also be allowed. And the time reverse of this process here is one where a portion of the mass of this object, big M, is converted into the kinetic energy of those two particles with mass little m. And so in processes like this, indeed, you are seeing that part of the rest mass of an object is transferred into kinetic energy and potentially usable energy. I should make one word about terminology here, which is that in many cases, especially in particle physics, we measure masses not in units of mass, but in units of energy. So we turn this equation, E equals mc squared, on its head, and we'll refer to the mass of some sort of elementary particle as some number times the amount times some measurement of energy divided by c squared. And for the purposes of particle physics, a convenient unit of energy is not the joule, but what is referred to as the electron volt, which is the energy required to accelerate or to move an electron across a 1 volt potential difference. You can imagine why in particle physics you're dealing with moving particles with charge, like electrons and protons, across voltage differences, through electric fields. So this would be a convenient unit of energy to have. So, for example, the proton, when people talk about the mass of the proton, people don't talk about the mass in kilograms, they talk about it in electron volts. And it's roughly 1 billion electron volts divided by c squared. And even you'll often hear particle physicists using units where c is equal to 1. And so they'll just say that the proton has a mass of 1 billion electron volts. And so that's about, if you put in the numbers, 10 to the minus 30 kilograms. The Higgs particle, which you may have read about, which was just finally confirmed at the LHC, has a mass of 125, 126, somewhere between there, giga electron volts. So that weighs about 10 to the minus 28 kilograms. You might wonder why it cost $10 billion to discover it was so small, but that's in fact precisely the reason why it was so expensive. I wonder if it was the most expensive particle. Probably. Any questions before I continue? Okay. So, the observation that although E and P are frame dependent, the combination E squared minus P squared C squared is not frame dependent, then leads very naturally to the following question. So, the question then is how, specifically, do the energy and momentum of an object transform under Lorentz transformations? That is to say, let's say that we have an object with velocity v prime as measured in s prime, where the frame s prime is moving with velocity v with respect to the frame s, then you could ask, how are the energy and momentum of that particle as measured in s related to the energy and momentum of the particle as measured in s prime? The answer, it turns out, is going to be very illuminating. Any questions before I continue? It's clear the question that I'm asking. Okay. So, the energy of the particle as measured in frame s prime is mc squared over 1 minus v prime squared over c squared. The momentum is, okay, you know what, I'm actually going to use a slightly different, I'm going to call that u prime, just because I want to call it u prime. Because I want to call the velocity of the particle in s as u, so I want to use a different symbol for that. Let's call it u prime squared over c squared. So that p prime is m times u prime divided by the square root of 1 minus u prime squared over c squared. And we now want to compute E and P, the energy and momentum, as measured by someone in frame S. So first, you need to calculate U, which is the velocity of the object, as measured in frame S. Okay, that we know how to compute. That's our old friend, the velocity addition formula. So if U prime is the velocity of the object in S prime, and V is the velocity of the frame S prime with respect to S, then U is 1 plus V U prime over C squared. And so, in order to calculate E and P, we need to calculate this relativistic gamma factor as a function of U. So, what is that? That's 1 over the square root of 1 plus U squared. So So it's 1 over the square root of 1 plus, sorry, it's going to get a little hairy here. I'll do my best. 1 plus the square root of u prime plus v over 1 plus u prime v over c squared, all squared divided by c squared. And then we can multiply the numerator and denominator of this formula by 1 plus u prime v over c squared to get 1 plus u prime v over c squared times 1 plus u prime v over c squared squared plus u prime plus v squared over c squared. Sorry, there's a minus sign. Okay. Is that why there was murmuring? There was, the natives were restless? Okay. Yes, there's a minus sign there, of course. So if you expand everything out, what do you get? You get 1 plus u prime v over c squared divided by the square root of what do you get? Well, you get 1 plus u prime squared v squared over c to the fourth minus u prime squared over c squared minus v squared over c squared plus a cross term involving u prime v prime that actually cancels. And so you get 1 minus u prime squared over c squared times 1 minus v squared over c squared, otherwise known as gamma of u prime times gamma of v times 1 plus u prime v over c squared. Okay. So, what is the energy as measured in frame S? Well, that's gamma of u times mc squared. So let me just write that out, plugging in this formula for gamma of u that I just derived. That's gamma of v times gamma of u prime times mc squared plus v times gamma of u prime m u prime. So let me just stare at that equation for a second. And remember that gamma of u prime mc squared is the energy as measured in the frame S prime, because the particle is moving with velocity u prime in the frame S prime. So the first term in the square brackets is E prime, and the second term is V times gamma of u prime m u prime. What is that? That is the momentum as measured in frame S prime. So E is gamma times E prime plus V P prime, where gamma here is gamma of V, namely the gamma factor associated with the transformation between S prime and S. Likewise, what is the momentum in frame S? Well, it's gamma of u times u mc squared. And what was u? Well, u was u prime plus v over 1 plus u prime v over c squared. So that P is equal to gamma of V times, well, this denominator here for U is going to cancel that term right there. So you'll get a gamma of U prime times U prime M Oh, I'm sorry, there's no c squared there. Again, you guys need to catch me when I make mistakes like that. So a gamma of u prime times u prime m plus gamma of u prime times v m. Or, to rewrite this, P is gamma of V times the first term. What is that first term? That's P prime. The momentum is measured in frame S prime. And what is that second term? It's V over C squared times gamma of U prime MC squared, otherwise known as E prime. So putting that all together, what do we conclude? We conclude that under a Lorentz transformation, energy and momentum transform exactly like t and x. The energy, if you have an object which has an energy and momentum E prime and P prime as measured in frame S prime, then its energy and momentum as measured in frame S are given by the formula E is gamma E prime plus V times P prime, and P is gamma times P prime plus V over C squared times E prime. And this is supposed to remind you, of course, of the standard form for a Lorentz transformation, so that delta t is gamma times delta t prime plus V over C squared times delta x prime. And delta x is equal to gamma times delta x prime plus V times delta t prime. I should make an important point here. The gamma factor that's appearing here is gamma as a function of V. And V is the relative velocity of one frame with respect to another. It's not the velocity of objects, either in the S frame or the S prime frame. What we're seeing here is that when you make a change of coordinates, that is to say, a change of reference frame, the energy and the momentum of an object change exactly as the time and spatial separations between events transform. And just as in the case of the Lorentz transformation of the space and time coordinates, we could make everything look a bit nicer by, instead of using the time coordinate t, we used a coordinate c times t. So just multiplying this equation through by c, and then rewriting everything in terms of the dimensionless ratio v over c, we could rewrite this formula in terms of, instead of p, the quantity c times p, and then you would see that the formulas look a little bit nicer because they're formulas transforming things which have the same dimension. Okay. The reason why the formulas relating for delta t and delta x are not the same is because delta t and delta x have different dimensions. But c times delta t and delta x have the same dimension. Likewise, e and c times p have the same dimension. So the formulas relating them are much more symmetric looking. Or, if we wanted to write this a little bit more compactly, we could write this in terms of the column vector containing as its elements E and CP as being related to the column vector containing as its elements E prime and C prime by the multiplication by that same friendly Lorentz transformation matrix, whose coefficients were the hyperbolic cosines and sines, whose argument was the rapidity phi, defined by the equation tanh phi is v over c. So the lesson that we have learned here is that just that energy and momentum of an object depend on the frame in which they are measured. But the way that they depend on the frame in which they are measured is not random. The way that they depend on the frame in which they are measured is exactly the way that time and space separations depend on the frame in which they are measured. And it turns out, although this is somewhat beyond, I think, the scope of this class, that this is really not an accident. There is a fundamental relationship between energy and time and between momentum and space, which is really a quite deep principle that underlies much of what we understand in physics. And so, although it's not something that I'm going to really emphasize in this class, because it would be a little bit difficult for me to explain in mathematical detail at this point, I should emphasize that it's really a deep feature of physics that the Lorentz transformation rules for energy and momentum are the same as those for space and time. Let me pause and see if there are any questions. One way I could say that a little bit is, have you guys seen Fourier transforms? Yes? Okay. If you know that momentum is the Fourier transform of x and energy is the Fourier transform of time. Okay. Have you guys seen that statement before? That makes no sense to you whatsoever. Okay. Just pretend I didn't say anything then. Are there any questions? I have 1 minute. No, I have 0 minutes. But I still have time for a question. Always time for questions. No questions. Okay, I'll see you on Friday.